Now, assuming you've been watching these episodes in order, you know about symmetric key algorithms. Now, symmetric key encryption is great stuff, and it's used all over the place, incredibly popular. However, symmetric key has one huge problem. The problem is the key itself. Remember, with symmetric key, you use the same key to encrypt and decrypt. And the danger is when you're like on the internet or the other person or the other thing is far away, how do you get the key to them? So to illustrate this problem, let me introduce you to Alice and Bob. Let me introduce you to my friends Alice and Bob. Now, Alice and Bob want to send each other encrypted data of some form or another. Now, it doesn't matter at this point what they're sending. Alice could be a web server and Bob could be a web browser, or Alice and Bob could be sending each other encrypted email, or they could be talking on Skype. I don't care what they're actually doing. They simply want to send each other encrypted data. Now, if we were to use a symmetric algorithm like AES, that's a great algorithm. The only downside to AES is that the same key that Alice is going to use to encrypt has to be used by Bob to decrypt. So how does Alice get the key to Bob? And that's where the problem comes in. Asymmetric encryption are vulnerable to people like Eve here, who are listening in. If Alice were to send the key via an email or something like that, then Eve could get a copy of it and she could decrypt our encoded information. So this is always a big problem with symmetric types of encryption. So in order to get around this problem, what we're going to do is we're going to come up with a completely new form of cryptography. This cryptography is not going to use one key, it's going to use two keys. Now just hang on a minute, this is amazingly cool. So what we're going to do here is that I will generate two keys. Now these keys are not physical keys, folks, they're just strings of ones and zeros. But these two keys with the right algorithm can do something absolutely amazing. So I generate these two keys on my computer. And what will happen is I will designate one of these keys to be the public key and another one to be the private key. This one's public because I can give this away to anybody I want, because the only thing a public key can do is encrypt. So if I want you to send me something encrypted, I will send out my public key. I'll send this out to anybody. Here, bad guy, you can have my public key, because the only thing you can do with it is encrypt stuff. And the only way you can decrypt it is with the private key. Now this private key I keep stored on my computer, actually in a little electronic vault, because I don't want this to ever get out. The only thing that this private key can do is decrypt stuff that was made by encryption using the public key. You get the idea? So we pass the public key out to other people. They encrypt their emails, they encrypt their web page, they encrypt their wireless or whatever it is. It comes to me and then I decrypt it. Now, if I want to send something encrypted, well, you have to send me your public key. Get the idea? So there's always going to be two keys. Now, isn't this fascinating? It is fascinating that you can come up with an algorithm that doesn't have one key. It's not symmetric. It has two keys, and one key encrypts and the other key decrypts. This is what we call asymmetric cryptography. Asymmetric is incredibly popular. For example, every time you get to a web page, you start with asymmetric to get your stuff going, and then once you're encrypted with asymmetric, you send a symmetric key, and then you just use symmetric from then on in. So it's absolutely fascinating how this works. Now there's a lot of different forms of asymmetric algorithms out there. But the first one, and still probably the most popular one, is called RSA. RSA is named after its three inventors, Rivest, Shamir, and Edelman. I hope I pronounce those names right. I never get it exactly right. And the idea behind RSA is that you use the concept of factoring. So when I talk about factoring, let's use like, I don't know, the number 12, okay? So if we take a look at the number 12, what numbers can we multiply together to make 12? So I could do 1 times 12, I could do 2 times 6, I could do 3 times 4, I could do 4 times 3, right? All of these different ways I can make 12. But there's a lot of numbers out there that can only be factored by themselves. So for example, let's use the number, oh, I don't know, how about the number 11? The number 11 can only be factored by itself. So 1 times 11 is all we can do. 11 is what we call a prime number. It can only be divided by itself or by 1. So what we can do, and this is what the RSA guys invented, they came up with the idea of taking 2 prime numbers. So let's take 11 times 17. So those are 2 prime numbers. If you multiply 2 prime numbers together, so we get 187, you create what's called a semi-prime number. A semi-prime number can only be divided by whatever the original 2 prime numbers are, as well as 1 and itself. Now, you would say, well, Mike, why is this good? Well, the answer is that there is no mathematical way to factor a number. The only way you can figure out what 2 numbers came together to make this number is through brute force. Start with 1, then 2, then 3, then 4, then 5. Now, with a number like 187, that's pretty easy, right? Well, let's make it a little bit harder. In fact, why don't we make it a lot harder? You ready? How about if we take a number, I don't know, how about a number like this? So you just go ahead and take your time and you tell me what the 2 prime numbers are that made this number. All right, you're not going to be able to do it. All right, maybe with a computer you could do it. Even that might take, a minute or two. But here's the answer, just so you guys know. So you'd say, well, Mike, computationally, I can still figure this out. Okay, well, RSA keys are up to like around 4,096 bits long, okay? So what I want you to do is take this, now this is a base 10 number, it's not a binary number, but look at a number like this. You're not going to be able to, in fact, go ahead, take all the supercomputers you want and take 100 years. You cannot calculate the prime numbers that this number is generated from. And that's the secret to all asymmetric encryption. Something that's very easy to do one way, multiplying 2 prime numbers together, but almost impossible to do the other way, which would be trying to factor a massive number like that. I don't even know what the number for that is. So using this concept of something that's easy to do one way and virtually impossible to do the other way, this is the cornerstone of what makes RSA work. Now, I'm not going to try to get into all the math of what makes RSA do what it does, but basically it works with 2 prime numbers that you multiply together to make massive, massive semi-prime values that are really, really hard for bad guys to figure out where they go. So let's go back to Alice and Bob and watch the beauty of asymmetric encryption making Eve's life very difficult. Now, Alice and Bob want to communicate via RSA asymmetric encryption. So the first thing they're going to do is generate each of their own key pairs. And this is done through whatever software is supplied for that particular application. And then they go about the process of exchanging their public keys. Now, keep in mind, if Eve grabs one of these public keys, it doesn't really make any difference because the only thing Eve could do would be encrypt something and then send it to somebody else for them to decrypt. But there is a problem, and that is, what if Eve pretends to be Alice or Bob? Well, the RSA people thought of this problem, so they included protocols as part of this encryption that handled, you ready, authentication. So what we would do in this particular case is that when Alice and Bob exchange keys, what they would do is they would add a little bit of extra information. They'd have the key, but along with the key, they would take a value, and believe it or not, they would encrypt with the private key. I know you're not supposed to be able to encrypt with the private key, but you actually can, okay? Normally, we only encrypt with the public key, but in this one situation, what we'll do is we'll take a little bit of data and encrypt it with the private key, and then we send this little bit of encrypted stuff along with the public key. You get it? And by working with the public key and running it through this little bit of information, it would confirm that the only place that this key came from is from whoever actually has the private key. And that's called a digital signature. Now, digital signatures and their big brother, certificates, are covered in great detail in other episodes. Right now, I just want to tease you a little bit and let you have an idea that things like digital signatures and certificates are really just ways we pass around public keys. But we'll hold that for a little while. Check out other episodes. Okay, so RSA's been around for quite a while now. And RSA started off with like 256-bit keys and 512, 1024, kept getting bigger and bigger. The challenge is that RSA with small keys is potentially crackable. So today, the folks who run web pages and stuff say that RSA should always start with 4096 bits. That's the smallest RSA key you should have. And that creates a problem, folks. These are big keys. Big keys take up overhead, big keys take time, and after a while it becomes frustrating, and we want to come up with a new form of asymmetric encryption that basically has smaller keys. What we now have is elliptic curve cryptography, or ECC. The beauty about ECC is that it provides really good security with much smaller keys. So for example, a 4096-bit RSA key could be replaced with a much smaller, don't hold me to these exact numbers because it's approximations, but around maybe a 256-bit ECC key. So ECC is very popular for that. ECC is based on, as the name implies, an elliptic curve. So the elliptic curve formula looks like this. Now, if I plug some values in there for the different variables, I could actually plot this on a graph, and here'd be one example of an elliptic curve. Now, what we do is we draw a line through the elliptic curve so that it intercepts the elliptic curve in two different spots. Now, the beauty of this is that if you have the formula and if you have one of the values, you can calculate the other place that that line intercepts the elliptic curve. But if you don't have that, you're not going to be able to do it. And that's the beauty of it. Just as we saw with RSA, we take something that's really easy to do one way, but pretty much impossible to do the other way. And the bottom line is that ECC allows us to have very, very small keys. In all probability, if you're accessing web pages like Google these days, or eBay, or Amazon, some of the bigger sites, you will be connecting not using RSA, but using ECC. So it's actually pretty cool. So the big takeaway here is that with asymmetric encryption, we're always going to have a public and a private key. For the exam, you're always going to say the public key encrypts and the private key decrypts, even though I did give you a teaser that for digital signatures, we can encrypt with the private key. But shh, we'll check that out in other episodes.